Okay. So once again, good morning, all of you, and welcome back to the online session of microprocessor and microcontrollers class. Okay, and this is the third class, and and in this class we'll be discussing about the architectures of microprocessors. Okay, so in the previous class we just started the introduction to microprocessors. That is, what is a microprocessor and what are different parts of a microprocessor, what is the definition of microprocessor and operation of microprocessor, how actually a microprocessor operates, that we have seen, and the architecture of microprocessor was also discussed briefly, right? So we'll be starting off from the architecture today, where we stopped in the last class. Okay, so this was the architecture that we discussed in the last class, which will be consisting of a CPU, which is nothing but a microprocessor, and then after an input device and an output device, and a small memory to store the data or instructions, right? In between or among these devices, among the devices which we have, like microprocessor, input output device, and memory, in order to communicate between them, in order to establish a communication between them, we'll have buses. We'll have what? Buses. Those buses carry the information or data from microprocessor to the output device, from input device to the microprocessor, from microprocessor to the memory. Okay, so this kind of transfer of information among the devices in the architecture of microprocessor will be done by the buses. And based on the type of function, based on the type of function they perform, those buses are classified into three types. Those are address bus, data bus, and control bus. Okay, so the bus which carries only address of the data, only address of the data, is nothing but address bus. So that is a unidirectional one. Okay, that is a unidirectional one. So the data bus will carry the data from microprocessor to the memory, from input device to the microprocessor, or from memory to the microprocessor. That is why the data bus is a bidirectional one. Okay, I have also given you the example why data bus is a bidirectional one. And next, control bus. This control bus performs or gives the control signals, gives the control signals to the CPU or memory or input output device. Okay, in order to perform a specific operation, in order to perform a specific operation. So that is why this is also a, uh, a bidirectional one. Okay, this is also a bidirectional one. I'll give you an example later in order to understand this bus structure very clearly. Okay, I'll give you a filmy example in which you can clearly understand. Okay, later at the end of the class I'll give you an example. Please stay tuned, right? And this was what we discussed in the last class. This was where we stopped. Now this microprocessor architecture is classified into three different categories, depending upon the depending upon the connection of these buses and different devices. Okay, so the basic classification is Van Neumann architecture, that you can see here, Harvard architecture, Super Harvard architecture. Okay, so these are the three architectures that are being used while manufacturing the microprocessor chip till today. Okay, that you have to keep in mind. Okay, these are the three architectures that are being used for the manufacture of microprocessor till today, right? So whatever the microprocessor that you see, that you find in your electronic devices, will be having one of these three architectures, right? The first one is Van Neumann architecture, The second one is Harvard architecture, and the third one is super Harvard architecture. So now let us see what are these architecture and how are these different from one another. Okay, so architecture means what? Physical construction, right? So these are different in the physical construction only. Okay, how these three are different in their physical constructions, that we'll see now, right? So first one is Van Neumann architecture. Okay, hope my screen is clear. It is a little bit duller because it is scanned. Okay, so it is a little bit duller, but anyhow it is clear, I hope. Right, so the first one is Van Neumann architecture. So Van Neumann architecture of processors is commonly used in the microprocessors. Okay, so the most commonly used one is Van Neumann architecture. Okay, most of the microprocessor manufacturing is done using this Van Neumann architecture, right? In this architecture, one memory chip is used to store both instructions and data. Okay, you can see the figure here. Okay, you just have a CPU, which is nothing but microprocessor, and you have a memory. You have a memory here. Okay, so CPU will interact with this memory, and this memory will get interact with the CPU. Okay, so for both the transfer of instructions and data, for both transfer of instructions and data, we'll be using a single memory. We'll be using a single memory. Okay, if that is the case, if you use a single memory for transfer of both instructions and data, then that kind of structure is nothing but what? Van Neumann architecture, right? So do not get confused between what is memory, what is instruction, what is data, how instruction is different from data. Okay, why we are using so many terms. Please do not get confused regarding this. Okay, I'll give you a clear picture of what is instruction and what is data in the coming classes. Okay, in the coming classes, right? Please do not worry about that. For the time being, please keep in mind that instruction is a different one and the data is a different one. Okay, so for the time being, in order to clear your confusion, I can give you a small example, like add 2 3. This is the thing we have, right? Add 2 3. Okay, I'll annotate for you. Just a minute. Just a minute. Charge అయిపోయింది. Just a minute. Right, friends. I'll annotate it for you. Suppose, let us say I have add 2 3. So I'm just trying to differentiate between what is instruction and what is data, right? So instruction means this is what called instruction, and data means these 2 and 3 are what? Data. These 2 and 3 are called what? Data. So instructions are nothing but commands. You might have studied in your C language or any other language. Okay, so most of you might be having an idea regarding commands, right? So instructions are nothing but what? Commands. Okay, the operations, okay, the operations that are being performed are nothing but instructions. Okay, these are also called operands. Okay, so these are the instructions, and these are called what? Data. Okay, so this is how you have to remember, right? So instructions should be there in the microprocessor. Instructions should be there in the microprocessor. Data has to be fetched from outside, because the instructions are specific to the microprocessor. For a microprocessor, the instructions are specific, because see, for language to language you will have a different instructions. See, for C language you have a different instruction, for C++ you have a different instruction, for Java you have a different instruction. Okay, and similarly for microprocessor to microprocessor you will have different instruction set. So instruction set is a package of microprocessor, but the data on which these operations are performed, the data on which these operations are performed is different. That is why the data has to be fetched from outside. Okay, so microprocessor will not have any specific data inside, right? Hope the confusion between instruction and data is clear. Okay, now what is this memory here? This is the memory which will be storing these instructions and the data. Okay, the memory is a slot or a space. Okay, memory is a space which will be storing these instructions and data. Okay, so every microprocessor needs some data or some memory in order to store these instructions and data. Okay, hope this is clear. Okay, okay, in the coming classes you will have a clear vision of these instructions, memory and everything. Okay, do not worry about that. For the time being, please keep these in mind. Okay, let us move forward here. So van Neumann structure will have a communication of memory for both instructions and data. Okay, the CPU or the microprocessor will be communicating with the memory only for both instructions and data. Okay, if that is the structure, that is called what? Van Neumann architecture, and this kind of structure is being used in most of the microprocessor architectures now, right? Next, if you move forward, the next one is Harvard architecture. So this Harvard architecture will have a different construction with respect to this van Neumann architecture. If you see here, if you see the diagram here, the CPU is communicating. The CPU is communicating with the data memory for the data. For extracting data, it is having data memory, and for extracting instructions, it is having program memory. That means the memory is divided into two categories here. The memory is divided into two categories. One for extracting the data, which is nothing but data memory, and another one for extracting the instructions, that is for program memory. So the data memory is a separate one and the program memory is a separate one. Okay, here both the memories are separated. If that is the structure, then that kind of architecture is known as what? Harvard architecture. Okay, so this you majorly find in microcontroller systems. Okay, when you deal microcontrollers, this you find that in microcontroller systems and in some advanced processors. Okay, in some advanced processors you find this Harvard architectures. Okay, so the advantage of this particular Harvard architecture is we can extract the instructions separately and we can extract the data separately. Okay, see here, I'll try to compare the things and explain you the advantages. See, in this van Neumann architecture, which you are seeing in this van Neumann architecture, when you want to extract the instruction, you can only extract the instruction. You cannot extract the data. Okay, you cannot extract the data because at a time we have a single bus here, we have a single bus here. Okay, so at a time we cannot extract both instruction and data. So we can only extract either data or instruction. Okay, so that is why this van Neumann architecture is little bit slower. Okay, because we cannot extract both instruction and data at a time, both instruction and data at a time. Okay, because the processor has to perform several lines of code. The processor has to execute several lines of code. Okay, if it executes one by one, one by one, one by one, it takes more time. Okay, so in order to overcome that disadvantage, we will have separate memory for programs, which is nothing but instructions, and we'll have a separate memory for data. Okay, so then we can parallelly extract this instructions from this memory and data from this memory. Okay, so parallelly the operations will be being done. Okay, so that is how we can speed up these processes. Okay, so hope the construction is clear and the difference and advantages are clear to you. Okay, right? So now the modification of this particular Harvard architecture, a little modification of this particular Harvard architecture will give you super Harvard architecture. What is super Harvard architecture? Okay, that is just a modification of a super Harvard, Harvard architecture. Okay, that modification is, you can see through diagram here. Okay, so you'll have instruction cache. You'll have instruction cache. So that will be stored in the CPU itself. That will be stored in the CPU itself. Okay, so that is the only modification from Harvard architecture to super Harvard architecture, and this structure is particularly used in digital signal processing systems. Okay, this is particularly used in digital signal processing systems, right? So that is about the architecture. Okay, so with this you might be clear with what is a microprocessor, what is the function of a microprocessor, and what is the architecture of microprocessor, what are different parts that we have in the microprocessor, and what are different architecture, different types of architectures that we have for a microprocessor. Okay, these things are very much important in order to understand the further things that we deal in this particular subject. Okay, hope these things are clear to you. And we have evolution of microprocessor. That means the next topic is evolution of microprocessors, which is nothing but a history of microprocessors. Okay, how these microprocessors are developed. Okay, uh, who introduced this first. Okay, these are all the things that we have to learn. So who introduced this, the first how many of 4-bit microprocessors we have, 8-bit microprocessors, 16-bit microprocessors, 32-bit microprocessor, and 64-bit microprocessor. These are all the things that we need to learn here. Okay, so these things we'll see next. Okay, right. So who introduced this microprocessors first? Okay, we'll see these things very quickly. So Fairchild Semiconductors, founded in 1957, invented the first IC in 1959. Okay, so that was the first integrated chip which is treated as what you can say IC, the first IC manufactured by the Fairchild Semiconductors in 1959. Okay, so in 1968, Robert Noyce, uh, Jordan Murray, Andrew Grove resigned from the Fairchild Semiconductor. So these were the persons work working in Fairchild when it was established, and after working for some period of time in 1968, these three people resigned from their particular Fairchild Semiconductors company. Okay, and they established their own company called Intel, Integrated Electronics. Okay, integrated electronics. Okay, so this was for the first time Intel company was established, and Intel company was established in 1968 by these three people. Okay, so Intel grown from three-man startup in 1968 to industrial giant by 1981. Okay, so these people started this Intel company as a startup in 1968, and they developed that particular company to an industrial giant. That means the topmost